All right, so we are now learning to calculate or practicing calculations for acids and bases. And we kind of took a step back into earlier units here because when we're doing acids and bases in Unit 9, we didn't actually, I usually gave you this concentration. We're actually having to calculate the concentration for this problem. But that gives us some more practice for the exam. That's good. All right, so remember that these brackets mean molar concentration. And molar concentration, that's the symbol we use for molar concentration or molarity, is moles of solute over liters of solution. Okay? So to figure out the molar concentration of this, we've got to convert grams into moles, and we've got to convert this milliliters amount into liters. Actually, you know what? Instead of milliliters of water, we need to make this milliliters of solution. Okay? To make this work out the way it should. There's some estimations we could make, but we're not going to do that here. Okay? All right, let's go sit down, okay? All right. Let's see. So, we need to know the molar mass then of nitric acid. So you've got to be able to figure out the formula. Nitric, there's no hydro on the front, so that means we have a polyatomic ion. And the IC ending comes from a polyatomic ion with an 8 ending. So we're looking for a nitrate ion. Go to your common ions list if you don't already know. If you don't already know and have it memorized what the nitrate ion looks like, and find it on your common ions list.
Right there.
Okay?
NO3.
So the nitrate ion is NO3 negative.
Negative. Right.
Acids always have hydrogen ions on them that have a 1+ charge. So I've got a 1+ and a 1 negative. So the formula we're going to come up with is HNO3. There's nitric acid. All right. Now I need to figure out the molar mass of this. I'm going to need that anyway to go from grams to moles of that, and we've got to have moles of that. That's the solute. That's the thing that's being dissolved. By definition, solute is the thing that's being dissolved. Solution is both a solute and solvent together. Let's see. We want to add up hydrogen and nitrogen and oxygen. Hydrogen is 1.00794. I've only got one of those. 1.00794. Nitrogen is I think 14.0067, I believe. Sure enough. I use this stuff a lot. You know, if you use them enough, you kind of know them by using them. 14.0067, and oxygen is 15.9994, and I have 3 of those. So 15. Whoop, turn it on. My help. 15.9994 times 3. 47.9982. Okay, so there's an empty slot over here to the right. And in addition, when you have an empty slot to the right, you're going to round off that number when you're done. Let's add up all these numbers first. So 47.9982 plus 14.0067 plus 1.00794, and we get 63.01284.
Booyah!
We're going to round off this last digit here, and we're going to get 63.01284 grams of nitric acid is equal to 1 mole of nitric acid. Huh? Oh, that's right. We have to round that off. You're absolutely right. Good for you. Good for you. Okay. Yeah, Jay Breezy's over here really irritating me here with his sad singing. It's just distracting me greatly. I can't keep up with stuff. Okay. For some reason, he's turned this happy Christmas song into a dirge. Okay. That's a song you sing for somebody that's dead. Please, Brian, stop.
Hey guys.
All right, I'm trying to be a little lighthearted, but it is irritating.
Yeah.
I don't know how it is for Ethan over there, but it's irritating to me. Okay.
We don't care about Ethan. Remember, we don't
Yeah, we don't care about
Ethan.
Ethan. Cares about Ethan. We'll steal his stuff. See? We care about Carl.
Give him his stuff back, please.
Tom, I think it's better for you.
All right, using the same process that we used in the earlier problem, when we were doing stoichiometry, we're going to put the same units and species on the bottom here as in this part of the problem.
Yeah.
And the other side of the equality statement goes on the top. And we want to cancel units and species. Units cancel, species cancel, like x's and y's in algebra. So we now have moles of solute. That's what we're looking for there. We want to put the liters of solution on the bottom. We don't currently have the liters of solution. We have the milliliters of solution. Well, let's go ahead and put it on the bottom. Okay, now I could put it on the bottom here, or I'm going to put it on, in this case, I'm going to put it on the bottom here. Either way works fine. 1 over 750.0 milliliters of nitric acid solution. Okay? So, to convert milliliters into liters, I need an equality statement. And what's the equality statement for 1,000 milliliters? Okay? So we want 1,000 milliliters on the top, so I can cancel liters, and 1 liter on the bottom. Okay, so now we are successful in getting moles of our solute over liters of our solution. We just have to do the math. So we want 1 times 1,000, which is 1,000, divided by 63.0128, and then divide by 750.0. We don't have to divide by 1. Okay? All right, so that gives us a concentration of 0.0211599722. Okay, and that's going to be moles of HNO3 over liters of HNO3 solution. All right, we want to underline our insignificant digits in our answer. And we're going to get 0.0212. The 5 makes the 1 round up. Moles of H. Well, I tell you what, moles of HNO3, which is the solute over liters of solution, is molarity, isn't it? Just an M, HNO3 solution. That's all we got to say. All right, that's the concentration of the acid itself. That's what we have right there. Okay, the problem up here asks for the concentration of HNO3. That's what we have. So that's number 1 right there. What about the hydrogen ion concentration? Well, using the Arrhenius theory of acids and bases, for every one of these, I'm going to dissolve it in water. Well, it's in water, but we get H plus NO3 negative. Okay. Moles on the top of the fraction here is a counting number. So for every one of these, I get one of those. Therefore, the moles on the top must be the same every time. And therefore, this concentration is going to equal that concentration. Okay? So, if the concentration of HNO3, because it's a strong monoprotic acid, and only because it is a strong monoprotic acid, every hydrogen ion dissociates. Remember our first lab in the acids and bases, we had to neutralize vinegar and a strong acid,
Oh, yeah.
and it took forever to do the vinegar?
That was all.
That's an illustration of this process. So if the concentration of HNO3 is 0.0212 molar, then the concentration of the hydrogen ion is 0.0212 molar. So this is Arrhenius. Bronsted-Lowry says if we take HNO3 and we dissolve it in water, we're actually going to move that hydrogen ion to something, in this case a water molecule. So the hydrogen ion actually leaves here and joins up with the water. So that on this side, water is H3O plus, because the hydrogen ion left but didn't take its single electron with it. So we get a plus sign here, that's aqueous. And once I take that hydrogen ion off, we have a nitrate ion floating around the water. So there's a 1-to-1 ratio again. Therefore, if the concentration of HNO3 is 0.0212 molar, then the concentration of hydronium is 0.0212 molar, but that only applies because this is a strong monoprotic acid. A single hydrogen comes off that, okay, and it dissociates completely. Yes?
Why, can you explain to me why the concentration of the HNO3 equals those?
Yeah, because they're right here. That's a 1-to-1 ratio. Every mole of this, let me put it this way, every formula unit of this, because this is strong, it completely dissociates. Every formula unit of this ends up producing one formula unit of this. Since moles are counting numbers, they're Avogadro's number of things, right? Then if I have Avogadro's number of this, when I put it in water, I'm going to have Avogadro's number of those, which means the molar concentration, the number of moles in a liter, is going to be the same. Does that make sense? Okay. All right. So that answers. This is number 2 up there, and this is number 3 up there. Okay. Now we're ready to go to number 4. So for number 4, we need this equation. We're trying to find the hydroxide ion concentration. And so this equation will get us there pretty quickly. The autoionization constant for water is equal to whatever that hydronium ion concentration is times the hydroxide ion concentration. Okay? The Kw is always the same number. 1.00 times 10 to the negative 14 molar squared. Okay? So we just plug and chug now. We know this number, we know that number, we can find that number. So 1.00, that number there, times 10 to the negative 14 molar squared, times the hydronium ion concentration, which we figured out was 0.0212 molar, times the hydroxide ion concentration, which we're going to figure out by dividing both sides by this, isolating the unknown. Okay. This is molar times molar. That's what molar squared means. And so we're going to cancel one of the molars here and the molar here, and all of this cancels. So we're ready to do the math now to find the hydroxide ion concentration.
Yes.
All right, we found the hydroxide ion concentration is 4.71698,113 times 10 to the negative 13. Okay. And we need to round that off to 3 digits. So we're going to get 4.72 times 10 to the negative 13 molar, because we've got molar left here. So that's the hydroxide ion concentration. pH. pH is the negative log of the hydronium ion concentration. So that's the negative log of 0.0212. So our pH is going to be 1.6736664139. Round that off to 3 digits. And we get a pH of 1.67. Okay. Now, there are no units on that, because remember, logarithms are exponents. And you don't have units, or at least at this point in time, we don't have any units on the exponent. Well, let's see, there's a couple of ways to find the pOH we're looking for up here. The easy way, since we're about to run out of time, is that 14 equals pH plus pOH. And since we know the pH, we're going to subtract that from both sides to find the pOH. So 14 minus 1.67 gives us 12.33 is the pOH. Okay?